Okay, you guys can see the screen? Yes? Yes. Okay, my talk is gonna be fairly quick, okay? So I think about 25 minutes. So this week I did not follow the book, okay? I follow some articles on the internet. Also, the Rare Skill ZK book, I found the EC part there is easier to understand. Okay, so let's start with the definition. We have Weierstrass curve, right? So the format is the equation y squared equals x cubed plus ax plus b, but you have to make sure the discriminant is non-zero. So all the points on this curve form a set, and we are working with a set full of points on curve. And each of the curve, so the xy pair, they follow the equation. So this equation, okay? So this discriminant non-zero requirement is to exclude the singular curve situation, okay? So if you have this zero discriminant, then it's hard to define like addition, the addition group law, okay? So we are excluding this zero determinant situation. The graph general looks like this. And also to make it a group, we have to define an identity element, right? So we define the point at infinity as capital O. So this point is just imaginary. So it comes from nowhere. We are just defining it for making this a group, okay? So we are making elliptic curve a group so that our group theory can apply to it. And so how do we define group law on EC is pretty intuitive. We are just connecting 2 points. For example, we are doing P plus Q. So we are just connecting P and Q with a straight line. It's gonna have an intersection with a curve somewhere at R. But we can say P plus Q equals R because that's gonna create some contradiction. You can try that on your own, okay? So if you define P plus Q equals R, then you have like a circular addition, like P plus Q equals R, P plus R equals Q, and Q plus R equals P. There is some contradiction there. So there is no way to define like group law if you just work with a straight line. We have to flip this R across the x-axis, okay? So we are defining P plus Q equals negative R. So this is just like a reflection over the axis of R. So we are connecting two dots and intersect the curve with some other point and then flip it over the x-axis, okay? So this is the definition. So this pretty artificial. It's not like a natural thing you find in nature. Okay, it's just like artificially we define addition on EC like this. Okay, so it's just like a definition. We just made it up somehow. Okay. Yeah, elements in the group is just points. Okay. Identity is the capital O, which is a like an imaginary point. Okay, so P plus negative P equals capital O. So this is something like zero, but yeah, it's like a point. Okay. So one thing that you should remember is with this addition definition, this group is an abelian group. So how do you prove it? The intuition is pretty easy. So you can see from the graph that P plus Q equals Q plus P. Yeah, this is the geometric interpretation. So they are generally just like a billion. You can see because P plus Q, the intersection is R, Q plus P, the intersection is R again. So they are the same, okay? So there are a few special cases. The first one is, what if you have P equals to 0? So this 0 is just capital O. I'm using this notation like randomly, okay? So this 0 is just a capital O, the imaginary point. So in this case, it's just identity. So like for some non-zero point R, so R plus P or R plus Q, in this case, is just R. So R plus P equals R. This is identity. So after you add P or add Q, you don't really change the value of the original point, okay? So second special case is, what if P is the inverse of Q? So geometrically, what I mean is they are just symmetric across the x-axis like this, okay? In this special case, if you do P plus Q, you get that imaginary point O, capital O somewhere. I just visualize it as like some point way up until here, okay? So you don't have to think like where this point is. It's just imaginary. So this is just like the identity element in addition, okay? So P plus Q equals O. The third special case is pretty interesting. This one is really bad in some sense, because we are saying P plus Q, we want to have an intersection R on the curve somewhere, right? But if you have P equals Q, then I mean, like geometrically is pretty hard to think of, but what I think of this is, imagine you have like 2 points really, really close to each other. For example, P is here and Q is somewhere here, for example, and you have some like calculus thing, right? You just push this Q to P little by little, right? So until somewhere that P and Q somehow overlap, then the line you draw is the tangent line. Yeah. So for this one, I think rigorously you have to prove it, but I just don't want to do too much formal proof on this, you know. So the thing is, there's a theorem saying if you have this, if you draw a line between P and Q in this case, then you must have an intersection somewhere, okay? So if you don't, so in this case, if you draw a tangent line, then you only have two intersections, this one, this one. So in the other case, you have three intersections. So there's a theorem saying the only possible cases are either two intersection or three intersection. There's no other special cases anymore. Okay. So yeah, if you want to prove it, yeah, just prove it on yourself. I don't want to do it. And so I said this special case is very interesting. Why? Because we can define scalar multiplication based on this case, okay? So if P equals Q, think of this as P plus Q equals P plus P equals 2P. So so this special case just leads to the definition of scalar multiplication, you know. So like the quote unquote multiplication on EC is just you do addition for n times. So basically n times P equals P plus P for n times, okay? And so some of you may ask, like, this is pretty hard to compute. If you just want to brute force the addition, like you do everything here, then it is gonna be pretty expensive. But there's an efficient algorithm called double and add, so that you can compute the scalar multiplication effectively. So how it works? For example, if we take n equals 151, so we are computing 151p. So the way how it works is like in DSA, this is called memoization, right? So you just break everything into 2 to the something power. You can always do this because you can decompose a decimal into binaries, right? So if you have like you just break it down into 0 and 1s, and you can just say like this is 1p, 2p plus 4p plus 16p plus 128p, right? So in this process, you are doubling it, but in only one like you only traverse the list once. So you are computing this. If this p exists in the formula, then you do add. Otherwise, you just skip it. For example, in AP case, we don't have AP here, so we just skip it, right? So if you have it, you double it and add the original value, and double and add, double and add. If the thing does not exist in the formula, you just skip it. Okay, so this is called double and add. Uh, so in theory, we are reducing the time complexity into O log n, because for each double we are read like we are, how to say that? I mean, for each double we are skipping like half of the possibilities, right? So the total computation it takes is just O log n. So this is pretty fast. Okay. This is double and add. So what we did is defining addition and scalar multiplication on EC. But remember that scalar multiplication is just a special case of addition. So when I first learned EC, somehow I thought it's a ring because it has two operations. That is wrong. Okay. So EC is a group. I mean, EC over R is a group. And this scalar multiplication is just to make things easier. So this is a special case of addition. The only operator you define in the definition is addition. Okay. We have those, and yeah, put a comment here. Just remember this is a abelian group. Therefore, the group theory we covered in previous weeks, they also apply to to EC, right? So the big theorems, everything, as long as it works for a abelian group, it works for EC. Okay, so learning group theory only simplifies your learning. You don't have to worry too much details about EC. Just think of it as a abelian group. Okay. Do we have questions so far? Oh, I see the comment in the comment area saying, what does fields of characteristic mean? That means you just add this, for example, p plus p plus p equals capital O, then the characteristic is 3. So it means like how many times you add to yourself, you get the identity. That's a characteristic. Okay. So if no, if no question, let's go to the next page. EC over finite field. So we just cover EC over R. In a notation wise, we can say EC over R is a collection of XY points in R2, right? Because both X and Y are from R. They must follow this equation. and they also have non-zero discriminant, and union the capital O, because capital O comes from nowhere. This is artificially added into a definition. Okay, so the graph looks like this. Why do we define EC over a finite field? Because if we are working with R, you can see for finding a point, you have to try like some random value for x, and then you take square root, right? So in the process, probably you're creating decimal numbers. So in general, in crypto and zk, we are only working with integers, right? It's pretty hard to work with a decimal value. So we are we choose to define this structure over a finite field. It turns out over a finite field, the computation is much easier than over R. Think of this. So for a finite field, we are limiting the addition. We are limiting the result in a finite set, right? So the maximum value we can get is p minus 1. So the computation is pretty efficient. And also there's one interesting property over a group with prime order, is that any group with prime order is a cyclic group. That is the one of the corollary of Lagrange, right? So cyclic group is generally more interesting than a building group, because we have many big theorems on cyclic groups. So you can see the notation is pretty similar. It's just mod p, right? So everything works mod p, and others are just the same. So after we put the mod p restriction on this group, the result we get is no more a curve, because now, like in the over R scenario, we have like continuous set of points, right? So in this case, we just have discrete points. So for example, this one is p equals 18, p equals 96. P just grows larger, and you can see the larger p is, the more points you have. Okay, so EC over a finite field is pretty hard to visualize, because it's just a set of points. But for simplicity, you can also just imagine EC over finite field. Yeah, you still think of this graph. It's pretty easier to memorize. Okay, but in reality, you are just working a set of points like this. Yeah, the good thing is, you see, over R, you see has some symmetry over the x-axis. Actually, over finite field, you have the same property. You see, symmetry here. This one, this one, this one, this one. You're not going to prove it, but yeah, you can play around it. Yeah, see this, like the reflection line is like here, so you have symmetry. Same for this one, but it's hard to see. Okay, here I'm making a claim. EC over finite field is a building group, and even better is a cyclic group. So recall that why is a cyclic group? Because we covered Lagrange last time. A corollary of Lagrange saying any group with order p, where p is a prime, then it is cyclic, and anything other than the identity is a generator. Okay, so for example, we pick like a random point on elliptic curve over finite field, then it is the generator, and we can generate all other points here in the form of ng. So this n is like from 1 to p minus 1, from 0 or no, from 1 to p. Yeah, like you can just traverse the like every point on the curve by keep adding g to itself. Okay, so in reality we are using bn 128. We are using bn 128. This is the name of the curve. So sometimes it's called bn 254. The difference is this naming convention means this curve has 128 bits of security, and this naming convention means it has the prime p has 254 bits. So they are just like different name for the same curve. So this curve has 254 bits of prime p, and the security is 128. Okay, so here's a great article if you want to read more about this curve. So this one is called like BN254 for the rest of us. Okay, so this is the article, you can read it. The field modulus is this huge number. So we are defining a curve that has a form y squared equals I cube plus 3 modulo the field modulus. So this is the field modulus. So everything, the computation happening here, the result is always bounded by this number. Okay. So field modulus is just is the prime p I just mentioned. So the form, if you have a curve with the form y squared equals x cubed plus b, where b is a constant, this is called the Bn curve. This is used by Ethereum precompilers. Okay, so therefore it is the most practical thing you can work with. And in fact, I constantly work with a library, PYECC, right? This library is written by Ethereum Foundation, I believe. This is like the official Python library for the curve. Okay, so the G1 here is pretty hard to explain right now because it works in bilinear pairing. But you can think of this as some generator of the curve for now, okay? You can add it like this. Add means G1 plus G1. G1 plus G1 is this huge number here. And you can assert that G1 plus G1 equals 2 times G1. So here's a gotcha here. Like you have to put G1 before 2, because it's pretty tempting to say multiply 2 comma G1, but yeah, that's wrong. And it took me some time to debug, right? So you have to put G1 first and comma 2. Yeah, this is just some implementation stuff in the library, pretty stupid. One thing to remember is that field modulus is not curve order. So in my experience, usually you want to work with curve order, right? Because in zk you are doing bilinear pairing for hiding the information, right? So you are working with G1, G2, and G12. So when you do operation on the EC over finite field, you have to worry about this curve order, not field modulus. Yeah, right. I constantly use this one. I never use field modulus somehow. Okay, so I had to remember that they are not the same concept. So field modulus means we are doing integer operations mod p, and this field modulus is that p prime. Okay, and curve order means how many points on the EC. So for example, you have let's say you have an example. Say there are, let's say, 20 points on the curve. Okay, so you are reaching 19G, where G is a generator. then you plus G to it, you got 20G. 20G is just capital O. Is that, yeah, capital O is that imaginary point, the identity, okay? So curve order means once you reach curve order, you just wrap around one circle and you go back to 0, and then you do the operations again, okay? One interesting property here is you can actually encode rational numbers. Yeah, this property is pretty interesting because think of a field. By definition of a field, everything other than 0 has inverse. So you can always find inverse to 3. So if you want to encode rational number, you can say, oh, so 2 over 3 is 2 times 3 inverse. And 4 over 3 is 4 times 3 inverse. And they always exist because this is a non-zero element in the field. And by definition, the inverse always exists. And how much is the inverse? Don't have to worry. You can do it in a using the Python function power POW. Okay. So this means the base is 3, exponent is -1, and we do that in modular curve order. Okay, so to encode 2 over 3, you can just say, oh, 2 times power of 3 inverse, and then you have to mod the curve order once again, because in Python this multiplication is oblivious of your curve order that you want to work with. Like this multiplication is over R, right? So you have to modulo the curve order once again outside. Yeah, this is pretty sneaky bug you probably make if you don't put this mod curve order here, okay? So we can encode 2 over 3 in this way. We can encode 4 over 3 in a similar way. If we want to try to assert that 2 over 3 times G1 plus 4 over 3 times G1, you got 2G1. This returns true, okay? So in some sense, I just want to show that you can do rational number operation in like a encrypted setting, because once we multiply G1, somehow we are quote unquote encrypt this number, because if I send you this number, you are not able to recover this number, right? Yeah, this is the EC-DLP hardness assumption we are going to cover next, okay? So yeah, just remember, like somehow EC operation like this, you multiply something with G1 is kind of like encrypt the data, but encryption I have to put like double quotes around it, because we are not really encrypting anything, because encryption requires a secret key. We are not using secret key here, okay? But yeah, you got my idea. Like this is already pretty close to the idea of zero knowledge. Pretty close, but not quite, okay? Question so far. Is an EC group over finite field always cyclic? Yes. The answer is yes. Actually, I tried to prove it, but it's pretty hard to find like a literature, like some easier proof for it, you know. Uh, I think it should be pretty involved to prove this fact, but you can just memorize it. Over, yeah, yeah, I claim that EC over finite field is always cyclic. So the property is pretty nice, pretty nice. Okay. Um, so let's continue. Oh, wait. I see another question asking, is because the computer having issue with floating point or some more fundamental thing? Floating point. I don't think the problem is a computer. I think the problem is Ethereum, actually. Because I know that there's a bug class called like precision loss, right? Like compound empty market bugs, like 100 finance hacks, that type of stuff. Um, Ethereum is using fixed point because it's easier to represent. Floating point, I heard it is pretty hard to do floating point arithmetic in like a blockchain setup because you have to reach consensus between different nodes, and you want that computation to give you a deterministic result over different computers. There's something wrong in the floating point computation in Ethereum. So the standard is using fixed point. Uh, Fixed point is just like you record like how many decimals are there, and you record the number as integer. For example, the integer I record is 1002, and I say decimal is 1. Then the actual number I represent is 100.2. That's just easier to work with, so it's easier to reach a consensus over the blockchain. Okay. Yeah, we are way off from zk. We are talking about some sneaky bugs. Yeah, that thing is pretty deep, the precision loss. Let's continue. Oh, this is pretty easy. I think I almost finished with my talk. Uh, we just said like we are using EC to encrypt data. Okay, so this is an application of it. Recall that last time we covered traditional Diffie-Hellman protocol. In traditional Diffie-Hellman, we were using the DLP problem. So DLP means I give you h equals g to the x mod p. For example, this value is what I distribute on the internet. Okay, I just send out this. I publish this information on my website, and then Eve, some malicious Eve, comes here and got this information. She wants to recover my secret X. Okay, so my secret is the exponent, and she wants to recover that. DLP says it is impossible to compute it. Okay, uh, so so that was the hardness assumption for Diffie-Hellman. So right now we are working with easy Diffie-Hellman. So easy Diffie-Hellman is just we are replacing this hardness, like this difficult property, with the elliptic curve. So how it works is just we generate a secret key. This is just some random integer. Okay, so random integer secret key for Alice. Bob generates a random secret key for himself, still a random integer, and then I compute the public key. Forgot to mention that we had to agree on a generator G that Alice and Bob must agree. Okay, this usually is published in a standard or something like NIST standard. Okay, we have a generator. We generate a secret integer for each person, and then for each of them, they just compute the random number times G. So this was the scalar multiplication we just talked about. Okay, so everything, of course, works in a finite field. So they have to define like a common shared field modulus as well. Okay. No, I mean curve order. Yeah, like a shared curve order. So they exchange the public key, and then in the end, Alice has PKB, Bob has PKA, and what they do is they just multiply their secret key on the encrypted data they got from the internet. Okay, just multiply, like this information what comes from Bob, and this information PKA comes from Alice, and then they just multiply this secret number to this info, and the correctness is pretty easy to verify that. So the multiplication here happens in a finite field, and that field is multiplication is a billion. We are just multiply, for example, like 3 times 5. This is 5 times 3. So yeah, it's pretty easy to see that in the end they compute a shared secret. Okay, so the security here is we are publishing this to public key on the internet. What if a malicious actor Eve comes in and extract this info and try to recover my secret key? This is the assumption of ECDLP. Because why is the assumption? Because we don't have efficient algorithm to compute it for now. But yeah, I don't think there's a formal proof saying ECDLP is how hard. But right now, the assumption is without quantum computer is impossible to break. For example, you give me SK plus G. For Eve, is impossible to compute SK if Eve does not have a quantum computer. Okay. So yeah, I'm promoting my my own article again. So this is my blog. If you are interested in like a small subgroup attack on the ECDH, you can read it here. Yeah, actually, I found this bug in a live. Oh no, not live. It's in an audit. Like a Web3 protocol, a pretty big name, but I can't reveal the name. I think it's under NDA or something. Can't reveal the name, but I found this bug in a like elliptic curve library. Okay, this small subgroup attack, pretty interesting. Questions so far? Oh, you guys are discussing this nasty floating point thing again. Oh my god. Let me read it. Oh, finance. No, I mean, this is pretty interesting topic. If you are a security researcher, you have to focus on this floating point thing. Like in Ethereum, it's fixed point. You have to focus on it, because like this year, I noticed like quite a few attacks in the real world. They just exploited this precision loss combining with some other properties, like ERC 4626 inflation attack or a compound empty market attacks, something like that. Yeah, they always involving some precision loss. Pretty important topic. So in the end of my talk today, this is the last page. Okay. This is very interesting. It's like a motivational zk example that, for example, I want to prove a really easy problem. Prover claims that I know xy, such that x plus y equals 15. Okay, this is just a toy example. So I have a prover, have a verifier. Verifier want the prover to prove it, but without sending x and y, because we are trying to achieve the zero knowledge property here. So what we can do is we can compute xg and yg. This is just a scalar multiplication over a finite field, and send it to the verifier. And verifier checks xg plus yg equals 15g. So As long as this equation holds, we have x plus y equals 15, but verifier does not know the value of x or y because of the hardness assumption of ECDLP, okay? Yeah, pretty interesting. You see the zero knowledge property is easy to achieve, but the problem is efficiency, okay? So right now we don't like walk through like the real world zk protocols for now, okay? We're gonna cover them next. So for now, we are getting this intuition. Yeah, so why are we studying elliptic curve? Because elliptic curve is connected to the zero knowledge property, but the problem is efficiency, okay? So yeah, just remember that. If you want to achieve like, if you just want to achieve zero knowledge but not succinct, yeah, you can just use bilinear pairing, I think. Okay. So another example, pretty interesting, is we can encode rational number. We just talked about that, okay? So prover claims that he knows x, such that 23 times x equals 161. Verifier says, okay, prove it, but don't give me x because we want to make it zero knowledge, okay? The prover just compute the inverse of 23. Yes, is always exists because we are doing it in a finite field. Prover computes so this number. So in Python is 161 times POW 23 comma -1 comma curve order. Okay, this he sends this this encrypted quote unquote encrypted data to verifier. Verifier just multiply 23 on the left. If the final result goes to 161G, we can confirm that this data is correct without knowing the actual value of x. Okay. Pretty insightful, but not realistic. This is the basic zk example. Okay. So for further study, I recommend you to check out the source code here. Also play with, yeah, PYECC. Pretty interesting. This is the official library implemented by Ethereum Foundation. Okay. Okay, that is my talk. That is my talk. You are welcome. I'm gonna stop sharing. Yeah, did Anna fix your screen sharing stuff?
Yes, that was the perfect time for me to fix it.
Oh, nice.
Well, great talk. Yeah,
Oh, thank
I
you.
think it was also good actually. Yeah, I think it was good that we switched it up because I picked
Yes.
like some examples where we can actually like compute things, and you gave like a very nice introduction to elliptic curves. So maybe there's still questions for your talk, but if you want, I can show the exercises I have with me. Yeah.
Yeah, yes, please go ahead.
Sure. So let's see, technical difficulties aside. Okay, I hope you guys see my screen. Great.